Welcome to the deep dive. Today we're jumping straight into the really fascinating world of generative models.
Yeah, these AI systems that can whip up realistic images, audio, text. It's pretty amazing stuff.
And we're zooming in on diffusion models. They're kind of inspired by physics, how particles spread out.
Right, and they've been incredibly successful, especially for, let's say, continuous data like images. I mean, think of all the stunning AI art out there.
Absolutely. A lot of that is thanks to Gaussian diffusion.
But then you have discrete data, like text, which is made of tokens, or even things like molecules.
And traditionally, the approaches for that kind of data have felt, well, pretty different, haven't they?
Totally. It's like there were these distinct families of models. You had Gaussian for the continuous side.
Yeah, and the things like uniform state diffusion models, USDMs, and masked discrete diffusion models, MDMs, for the discrete stuff.
Exactly. They seem like separate worlds tackling similar goals, but with different toolkits.
Okay, so that sets the stage, and that's why today's deep dive is so interesting, right? We're looking at a paper that found a link.
Precisely, a fundamental connection. They actually call it a diffusion duality. It suggests the discrete process isn't just separate. It can actually emerge from the continuous one.
Wow, okay. So our mission today is really to dig into this duality, understand how they connect.
And crucially, how this isn't just some neat theory. It leads to real practical improvements for these discrete models, especially USDMs, making them faster, making them better.
So expect some surprising insights and hopefully some really practical takeaways by the end.
Definitely. The core discovery itself is, well, quite something. The paper shows that this discrete uniform state diffusion process, it doesn't just run parallel to Gaussian diffusion.
It emerges from it, is that what you're saying?
That's the claim, that there's an underlying continuous Gaussian diffusion process, and the discrete one sort of arises from it.
Oh. How does that work? It sounds almost like the discrete data is a kind of shadow of the continuous process.
That's actually not a bad way to think about it. The bridge, the mechanism linking them, is an operator called argmax.
Argmax, okay.
So imagine you've got a vector of continuous numbers from the Gaussian world. Maybe they represent scores or probabilities for different possibilities.
Right.
Applying argmax is simple. You just find the index, the position of the largest number in that vector.
Ah, okay. So you take all these continuous possibilities and just pick the single winner.
Exactly. And that winning index directly gives you your discrete value, often as what's called a one-hot vector, basically, a list of zeros with a single one at the winning position.
So it turns that smooth, continuous output into a sharp, single discrete choice.
Precisely. And the paper shows this isn't just a one-off trick. If you apply argmax to the variables throughout the entire Gaussian diffusion process,
The whole thing transforms.
yes, it transforms the marginal distributions of the Gaussian process into the marginal distributions you'd expect from a standard uniform state discrete diffusion process.
Okay, marginal distributions. Let's just clarify that a bit. What does mapping those mean practically?
Okay, think of the distribution at any point in the diffusion as like a cloud of possible states. The marginal distribution is sort of like looking at the shadow of that cloud projected onto one axis, or looking at the overall probability landscape for just one piece of the puzzle.
Got it.
So the finding is, apply argmax step by step to the continuous variables and the overall pattern of where the resulting discrete variables land. It matches the pattern you get from the standard discrete diffusion model.
That's really neat. The underlying structure gets translated from continuous to discrete via argmax. Is there a mathematical consequence of this?
Yes, and this is where it gets really interesting theoretically. There's a theorem in the paper, Theorem 3.1. It establishes that the evidence lower bound the ELBO.
Right, the ELBO, measure of how well the model's learning.
Exactly. The ELBO for the uniform state discrete diffusion is actually tighter than the ELBO for the underlying Gaussian diffusion it came from.
Wait, tighter. That seems backward.
It does.
You'd think going from continuous to discrete with argmax would lose information, maybe make the bound looser.
That's the counterintuitive part. It suggests that this derived discrete process somehow gives you a more precise or maybe a more constrained handle on the likelihood of the data compared to the original continuous process it emerged from. It's mathematically cleaner in a sense.
Huh. That is surprising, getting a sharper view through what seems like a simplification.
And this isn't just theoretical navel-gazing. The researchers took this duality and built a framework around it. They call it DUO.
DUO, okay, name for the duality, I guess.
Seems likely, yeah. And the goal with DUO was basically to port all the advanced techniques developed for Gaussian models over to the discrete side, specifically for USDMs.
To make them better, faster. Especially for language models, right? They wanted few-step generation.
That was a key target, and they made some serious headway. Let's talk about training first.
Okay. Creating discrete diffusion models. It's often been a bit slower, maybe less stable than the Gaussian ones.
Yeah, generally less efficient. So Duo introduces this clever curriculum learning strategy.
Curriculum learning.
Yeah.
Like starting easy and getting harder.
Exactly. Because they know the discrete process is linked to the Gaussian one via argmax, they exploit that. They use a smooth approximation of argmax, something called tempered softmax.
Tempered softmax.
And they anneal a temperature parameter during training. Think of annealing like slowly cooling something down.
So how does that help?
Well, at the start of training, with a high temperature, the tempered softmax is very smooth. It behaves a lot like the simpler continuous Gaussian objective. It's an easier target for the model to learn initially.
I see. You start Gaussian-ish.
Right. Then, as training progresses, they slowly lower the temperature. The softmax gets sharper, closer and closer to the actual hard argmax function. So the training objective smoothly transitions from the easier, continuous-like task to the standard, harder, discrete one.
Guiding the model along a smoother path. Makes sense. What kind of results did they see from this?
Pretty significant ones. First off, it doubles the training speed, a 2x acceleration.
Wow, double speed. Researchers love to hear that.
Oh, absolutely. And if you look at the paper's results, it also massively reduces the variance in the gradients and the loss during training. Makes the whole process much more stable.
Okay, so faster and more stable training. Did it lead to better models in the end?
It did. Duo achieved new state-of-the-art results among USDMs. It's also really competitive with those other discrete models, the MDMs.
Even against standard autoregressive models.
Yeah, it actually beat autoregressive models on 3 out of 7 zero-shot language benchmarks they tested. And they did an ablation study, taking parts away to see what matters. And this curriculum learning part accounted for roughly half of the performance gain Duo had over previous USDMs. So it's a really core component.
Okay, that covers training. What about the other big bottleneck for diffusion models actually using them, the sampling part? Getting the text or image out. That can take ages.
Right. That's often the killer, especially for discrete stuff like text. Ancestral sampling, the common method, often needs hundreds, even thousands of steps. We talk about NFEs, number of function evaluations. High NFEs mean slow generation.
But there have been ways to speed up Gaussian models, right? Like consistency distillation.
Exactly. Consistency distillation, or CD, was a huge step for continuous models, letting them generate really good samples in just a handful of steps, sometimes even one.
And the duality let them bring this over to the discrete side.
That's the beauty of it. Duo adapts consistency distillation, they call their version DCD, for discrete consistency distillation, leveraging that underlying continuous connection.
So consistency models let you jump almost straight to the end result, bypassing many steps.
In essence, yes. They enable deterministic generation in a fixed, small number of steps.
How small are we talking? What's the speed up here?
It's dramatic. They reduce the number of sampling steps by 2 orders of magnitude.
2 orders, so like 100 times faster.
Yeah. They went from typical numbers like, say, 124 NFEs down to just 8. 8 steps, with minimal loss in the quality of the generated text.
Okay, hold on. Any 24 steps down to 8. That's game-changing for usability.
It really is. Imagine going from needing over 1,000 computations to generate a sentence down to just 8. It opens up totally different possibilities for applications.
How does this compare to other attempts at speeding up discrete models, like maybe distilled versions of those MDMs?
This is where Duo really shines, especially if you need results really fast, what they call the low NFE regime.
Using just a few steps.
Right. When you're down to, say, 8 or 16 steps, Duo significantly outperforms the distilled MDMs. The quality holds up much better.
And is there a reason why? Why are these USDM-based models like Duo better at this super fast few-step generation compared to the MDM approach?
Yeah, there's a really interesting underlying reason. It boils down to how the models actually work during the reverse process, the generation. USDMs have this property researchers call self-correction, as the model generates the text step by step, refining it from noise. The individual tokens, the words or parts of words, can still change based on the context that's emerging around them.
So it can fix mistakes it made earlier.
Exactly. If it puts down a slightly wrong word early on, but later steps suggest a better fit, it can revise that token. It corrects itself as it goes.
Okay, and MDMs?
MDMs often work differently. They typically involve unmasking tokens. They predict missing parts of the sequence, but once a token is unmasked, it's often locked in, fixed.
So no going back to change it later if the rest of the sentence evolves.
Generally, yeah. That lack of flexibility can hurt them when you force them to generate in very few steps. Early mistakes get locked in, and the final result might lack coherence because there wasn't time or opportunity to revise.
So the self-correction ability of USDMs, which Duo leverages, makes them inherently better suited for this rapid few-step generation. It's like sketching lightly versus using a permanent marker.
That's a great analogy. The ability to revise allows for better overall quality when time is short.
Okay, this is fascinating.
Yeah.
Let's pull back a bit and connect this to you, the listener.
Yeah.
Why should you care about diffusion dualities and USDMs versus MDMs?
Well, I think this deep dive really shows something important. Finding these deep theoretical links between different AI approaches, even ones that seem quite separate.
Yep.
It's not just academically interesting, it can lead to really powerful practical breakthroughs.
Yeah, like that faster training, doubling the speed. That means researchers can iterate faster, try more ideas, build better models quicker. The whole field moves faster.
Definitely. And the faster sampling, that 1,000 steps down to 8, that directly impacts potential real-world use.
How so?
It means you could realistically use these very advanced, very capable generative models much more efficiently. Maybe on devices that aren't supercomputers. Think about running powerful text generation on your laptop, maybe even your phone eventually.
Or using them in interactive applications, right? Like chatbots or creative writing tools where you need a response now, not minutes later.
Yeah, exactly. Waiting for thousands of steps just isn't feasible for interactive use. 8 steps, that's potentially instant.
And I think that insight about why USDMs work better for few-step sampling, that self-correction thing, is key too. It shows it's not just about throwing more compute at things.
Right. Understanding the actual dynamics, the underlying mechanisms of how these AI systems work, that's crucial for designing models that are not just powerful, but also efficient and reliable enough for practical deployment.
So you're not just getting facts here. You're seeing how fundamental discoveries translate directly into better tools.
So wrapping it up, the core idea we explored was this powerful concept of a diffusion duality.
Yeah, the idea that discrete diffusion, specifically the uniform state kind, isn't really separate from continuous Gaussian diffusion. It can actually emerge from it through a simple operator like argmax.
And crucially, this isn't just some elegant mathematical footnote. The Duo framework showed how to leverage this duality for huge practical benefits.
Doubled training speed for USDMs.
And that dramatic reduction in sampling steps, from over 1,000 down to single digits, making them highly competitive, maybe even superior to other methods like MDMs, especially when you need generation to be fast.
It basically gives you a bridge to bring all the clever tricks from the well-studied continuous domain over to the discrete world.
A very useful bridge indeed.
Which leads us to a final thought, something for you to maybe chew on after this.
Yeah.
If these diffusion models for continuous data, like images, and discrete data, like text, which look so different on the surface, if they turn out to have this deep underlying connection.
What other areas are out there? What other seemingly disparate models, maybe even concepts from completely different fields of science, might be hiding similar fundamental dualities?
Yeah, if we find those connections, what kinds of breakthroughs, what new capabilities could those undiscovered dualities unlock? What happens when we find the next bridge?